Hey Rex. Hey Ben. How's it going? Green Bunny? Where? Where? Okay, what am I doing here? I think I'm doing this today. I finished Vitali last time, so I think this is the only thing left for this stuff, the consequence of non-measurable sets. And then I wanted to change notations that I used for the rational equivalent sets. So before I do that, might as well just finish this since it's very quick. This is what? Resolved 2.50. All right, 2.50. It's a pain to write directly on the desk. Okay. Okay. There are disjoint sets of real numbers. I feel like I can just... There are disjoint sets A and B in, oops, contained in R, or subsets of R. Okay. Finally, a short proof. So if there were not two such sets, then by the definition of measurable set, every set of real numbers would be measurable, which contradicts the preceding theorem. So if this didn't exist that satisfied this inequality, then this is it's not measurable. Okay, the proof is short, but the the, the understanding is gonna take me a quick second, or maybe a long second, because I completely forgot what I did here. Not completely, but I haven't looked at this since last week. Okay, If E is a set of real numbers with a measure greater than 0, then there exists a subset of E that is not measurable. Okay. And if E is measurable, there exists a subset of E that is not measurable. Definition of measurable set. Every set of real numbers would be measurable. Okay, the definition of the measurable set has to do with the sum. It's this here. Okay, let's write it down. So set is measurable if it satisfies this equality for all A. Okay, what are we trying to do here? So Vitali gives us an existence of a set E that is not measurable. Okay. Just realized I don't have music. Like, why is it so quiet? The heck? I didn't even notice you guys sent messages. Like, I have my I have my phone out for messages and it's like not showing any messages. Your screensaver? Oh, my screensaver. Let's see. Um, just finishing up proving the linearly independent eigenvectors that come from distinct eigenvalues remain linearly independent when you union them. Are you proving this for like a series or for? Because I know you're tutoring somebody or helping someone with linear. Hey, Wisdom me, how you doing? I don't know when you sent this message. Oh my gosh, what's going on with my phone? Okay, let's see. Okay, now the messages are showing. One of these days I'll get another monitor. I don't have to stream all bootleggy. Let's see. I thought this would be much easier to grasp, but for some reason my brain does not want to understand what those two lines are saying. Okay, if there were not two sets, so if there didn't exist disjoint sets, disjoint sets whose union is just less than the measure of the union is less than the measure of the individual sets, the sum of the individual sets. The definition of measurable set, every set of real numbers would be measurable. How does this definition give us every real number is measurable? Let's see. Oh, I see. I see, I see. This would be so this is for all A, for all subsets A of R. This is true for all subsets A of R. And so you can actually write this, you can rewrite this as, actually I'm just gonna write it in the proof. Okay, so suppose suppose there isn't, or there are no, suppose there are no disjoint sets in R. Okay. The wait, not done yet. That's not the sentence. Um, How do I write this so this comes out perfectly? Suppose there are no disjoint sets A and B, which are subsets of R, such that this is true. Okay. So obviously this is a contradiction proof, and we're supposing the opposite of the conclusion. So by the definition of measurable sets, and then I can use this, but I'm going to renotate this because A's already been occupied. So we can write this as let's use omega. For all omega, that's a subset of R. But omega is omega can be written as the union of these two sets. Yeah, I think this is good. Ahoy. How's it going, Phobos? I saw you're making a game earlier. Or so this is true. We can write omega as a union of these two sets because they're disjoint, and it basically slices omega. Yeah, it slices omega into disjoint sets. It's good. Oh, pen and paper game into a Twitch integrated game. Nice. Yeah, it looked interesting when you were working on it. I wonder how much coding is going to be. or any measurable set E. I hosted the game session once before and it was quite fun, but a lot of work. Yeah, I got the impression that you did this before. On Twitch? Was it on Twitch or was it like a in-person sort of event? R Oh, on Twitch. Interesting. I write code for a living, so the quantity of code isn't too prohibitive. It's just about finding time. I see. Are you going to do this during stream? Are you going to write the code on stream or is it going to be like off stream? I think I proved earlier that R, like there's always a measurable set. I think there always exists a measurable set. Because R, right? If you take the whole real numbers, I think that's always measurable. Let's see. Where is it at? Outer measure. This one. Hmm. Oh my gosh, I still have to fix this. No. Okay, okay. Yeah, the universal set is measurable. Always. Hmm. I mean, we're specifically working on R for this proof, and we've proven a lot of sets are measurable, and so there definitely exists a measurable set. So I guess I can write we've shown. Yeah, we've shown plenty of measurable sets. I'm a little bit lazy about like referencing which one I want to use. On R. Therefore, exists. Okay, so if we let A equal to sigma intersect E and B equal to, so this implies that the measure of A union B, the outer measure is equal to the measure of A plus the measure of B. Okay, so we have the equality set up from the definition of outer measure. This is with A and B disjoint. Yes. So A and B are disjoint here. Um, okay, we're very close. Okay. Okay, and I need to show that every set of real numbers is measurable from this. Why am I not getting this? Oh my. Okay. Do we know m star of the Vitali E? Do we know m star of the Vitali E? What do you? I'm not sure about Vitali E. Hmm. I'm pretty confident that this is the right strategy, is to decompose this into the union. But why does this imply that every set is measurable? So this is for all sets and subsets of R. This is for all subsets of R. Hmm. Yeah, I did this problem. It's so interesting when I decide to do something because I just feel like doing it. It just ends up being a problem anyways. Let's see. So somehow this gives us that all subsets of R are measurable. And then once I get that, Vitali is gonna give the contradiction. Vitali shows that there exists a non-measurable set. So for every subset of R, we have that the measure of omega, the outer measure of omega is equal to the outer measure of the intersection of omega and E, where E is a measurable set, and plus the outer measure of omega and the intersection of the complement of E. Hmm. Yeah, this sucks. It sucks that this two-liner is stumping me. Oh shit. Why? Why you gotta do this to me? Alright, let me see if the older edition has something, has it phrased a little different. It's my book. Okay. Oh, interesting. Yeah, it actually does write it out. I don't know why they take it out of this edition. Just to save another line? Okay. Okay, then. For every disjoint. So for every disjoints, I feel like this phrasing is a little awkward for all disjoint sets. We have this. It's actually, I think the book writes it as an equals, but I think if you're taking the, I think if you're taking the negation of the statement, it should be greater than or equals to, right? This is always true. The less than or equals to is always true, uh, no matter what, by a theorem that is proved earlier. And so the negation of this statement, it should be greater than or equal to. And so if we assume this and we already have less than or equal to, then we get equality. Then for all disjoint sets A and B and R, we have the outer measure of the union of A and B is equal to the outer measure of A plus the outer measure of B. Okay. Um, Okay, from this, the book basically says that this leads to every set being measurable from the definition of measurable sets. Okay, I'm it's that's it. I'm still stuck on that part. And so the definition of measurable sets was for every set omega. So this is the part where it's where that dictates if it's measurable, if it satisfies this inequality. So a set E is measurable if it satisfies this equality right here. Okay. Is there something I can do with this? Oh, what am I doing? I'm even writing notation correctly. Is there something else that I'm missing? Sigma algebra of measurable sets. Maybe there's another result that I can use. Okay, so this corollary tells me that if we have disjoint measurable sets, we get this equality, but not the reverse. If it told me the reverse, it would that would finish the proof. Hmm. Oops. Okay, I need to somehow use this to show that for any arbitrary e and arbitrary omega, we get this equality. Oh, that's okay. Yes, I figured it out. I figured it out. Okay, so how do I do this? Just want to keep this somewhere so I have like some sort of vision on it so that I don't lose track of my thoughts. Okay, so the way we do this is um, we let we basically let omega and um, e be any set, any subset of R. Okay, so if we let omega and e be any subset of R, then um, then we can write omega as the union of omega intersect E, union omega intersect E complement. Okay, so thus, I'm gonna go to the next page because I'm gonna finish soon anyways, and I don't want it to spill over like one line in the next page. So what does this tell us? It tells us that the outer measure of omega, which is just equal to the outer measure of this union, so we're just writing the details, intersect E, union omega intersect E complement. Okay, and then basically by the hypothesis that we imposed, um, this has to equal to the outer measure of omega intersect E plus omega, the outer measure of omega intersect E complement. So this is because these are disjoint sets. Okay, so these are disjoint sets, so we get this. And so since E and omega are any arbitrary set, then we've shown that every set in R is measurable. We've shown that any, yeah, I can erase this now because I don't need it anymore. So we've shown that any subset of subset. Well, I'm going to be a little specific so that it's clear. I need subset E of R is measurable. We need arbitrary for omega because that is required by the definition of measurable sets. You need an arbitrary omega for the left side, and then the sum and the intersection is like the one that's associated to the measurable set. So shown E was arbitrary. We picked arbitrary E and showed that we constructed this equality which defines measurable sets and show that any subset of R is measurable. And then this is where our contradiction comes in. So this is a contradiction. My gosh, why is it doing this? It's a contradiction to Vitali's example, but I'm going to reference the result, 2.49. Okay, and so that's the end. Thus, there are disjoint sets. I'm just going to copy this. Oh man. Copy. Paste. All right. That took way longer than I expected, but I'm glad I got it. Yeah, that was a lot harder than I expected. My gosh. A freaking two-liner. A two-liner. I had to rewrite this two-liner into like 3, 4, 5, 6, basically like 6 or 7 lines. Hey Babs, how you doing? I'm proud of thee. Clap, clap, clap. Thank you, thank you. Oh man, that was insane. I did not expect this to be this hard. I was like thinking I was thinking last time when I finished my tallies, I was like, ooh, the next result is only 2 lines. It should be easy. And I turn on stream today and I'm like, all right, let's get this one done. And I get stuck for how long? Maybe an hour? Oh man. That was a Monka situation. How you doing, Pabs? Okay. So we basically showed one of the major issues with outer measure, and the issue is equality. We can't get equality for every set. Um, so the beginning of this chapter kind of goes over like the things that we want. The things that we want from this idea of measure. So we want that the measure of the interval to be the length of the interval. We want translation and variance. We want the measure to be countably additive over disjoint sets. I figured there was another one. There was one more. I'm pretty sure there were four. Let me see. Where is this? Got to reference the book that I used when I took this class. What is this? Okay, interval, uh, countable additivity, disjoint, translation and variance. And then the fourth one is that the measure is a function from the set of subsets of R to zero to the set from 0 to infinity. So the positive numbers including 0 and infinity. So if you're wondering what I'm like referencing here, I am referencing this book. And where am I referencing? I'm referencing somewhere. Hey, measurable functions. That's what I'm going to do soon. Where is it at? So we basically gone over this in this book. It kind of just goes over, it's not like separated like in the Royden book, because this book doesn't go over measurable sets. Now, where is it? This is the four. We ideally want these four properties for measure. And it turns out you can't get all four at once. So you kind of prioritize the ones that you want, which is in this case A, B, and D. We get these things, and we sacrifice sub-additivity for outer measure. And then we found out that if you just work with measurable functions, you actually get C as well, but you have to restrict it. Good, just went under the knife at the dentist. I'm good. Oh my. That reminds me, I need to go to the dentist soon. I need to do my yearly cleaning. Hey Luna. How you doing, Luna? I'm glad that's over. Yeah. Always scary to go to the dentist. Um it did. I just look like Kylie Jenner. I'm good, just organizing my closet. Cool, cool. Is it a huge closet? You sifting through clothes, deciding to donate, or or is it just kind of like a huge mess? Okay. So for outer measure, for the construction of outer measure, we don't get countable additivity, and we just showed why. Because there exist disjoint sets that are not measurable, and then that implies that we can't get the equality by the theorem we just proved. Okay, what did I want to do here? It's not a huge closet. It's just not messy. I just want to be able to get what I need faster. I see. Okay. Well, I hope that's not too much of a hassle. I know organizing stuff is like time consuming. So I made a mistake here last time. This should be prime. I caught it while I was kind of asking um, for someone to review this or look over it. Um, so I got confirmation that this is correct, but it just doesn't, the construction doesn't like, the way it's written out is kind of confusing. So what I'm going to do is I'm going to just rewrite things a little. We have an E and R, let X be an E. And then what we're going to do here, okay, so what we're going to do here is we're going to let, what's the construction work again? So we're not going to let X be an E. What we're going to do is we're going to let X, we're going to let the set equal to all of the Y's in R such that X minus Y is rational. And so this, if I remember correctly, this is the common notation for what was the freaking terminology? I'm forgetting everything. This is the equivalence, right? The brackets are usually reserved for equivalences. And then what we can do here is let A sub X be the intersection between X, or this equivalence set, and E. Yes, yes. The new Pabs. I'm about to be done soon, just taking a little break. Oh, nice. That's cool. Okay. So I can basically erase a lot of these things because this is me just trying to build like construct the sets that I want to work with for the Vitali example. I don't even need this prime anymore. The issue that I had with this that I wanted to check was the way I was constructing it looked very it looked countable, I guess. It was looking very countable for me because I was doing it one by one. Like I was first picking an element in E, which I call X, and then I build a set from that using the equivalence relation on E, the rational equivalence relation. And then I pick another element that's not in that set, that's still in E, and then I build another set around that using the rational equivalence relation. And then the process kind of continues in that fashion. And when I constructed this last time, it sounded like I was constructing it in a countable way, and I wasn't 100% sure if that's what was happening. And the issue with that is that these sets don't need to be countable. Because of the axiom of choice, I was very confused when AOC was elected to Congress. That's funny. Yeah, I actually did also make that comparison. Um, when I heard of the axiom of choice, I was like, hey, wait a minute. That's abbreviated to AOC. We need the axiom of choice in the government. Axiom of choice for president. If you like axiom of choice. I know there's some haters out there. Okay, so I think defining it this way is a lot cleaner because now we can construct E. Um, we can construct E like this. So in this case, I would need to use so this would be E is basically the set, the union of the X in R, it looks like. This was the issue that I had. Like I knew the index was a subset of R, not necessarily a countable subset. And then we have the union of this. Okay. I'm pro-choice. I want to be able to cut up an orange and reassemble it into two triangles of the same side. Nobody would ever go hungry again. Let's see. I'm losing my train of thought. Hold on one second. What did I gonna say? Um, let's see. What was I saying? The Banach-Tarski reference. I should feel ashamed about this, but I don't know these I don't know some of the big theorems, you know. Eventually I will have it. I do remember this, but like because I don't use it that often, it's just like, oh my gosh, not this thing. And if I remember correctly, this is like because of the axiom of choice. Yeah, it can be proven using the axiom of choice. Yeah, that would be great. That would be great if we can if we can apply that to like real life scenarios. Publication format. Yeah, stuff like that. This is like makes me. This makes me it makes me so uncomfortable. Like this is like this gives me like the 0 is equal to 1 vibes. I'm just looking through the Wikipedia, seeing if there's like any um like physical examples. Banach-Tarski's paradox is one of the more counterintuitive consequences of the axiom of choice. Lets you chop up a sphere into 5 pieces, do rigid motions, and reassemble into 2 spheres the same size. The problem is the two sets are not measurable. Oh, wow. Five sets rather. Gotta run. Good luck. Thanks for stopping by. Does this book actually go over this paradox? No, it doesn't. Yeah, that's strange. That is like the second or third time I've seen that paradox. I think a few more times then I'll remember it. Just a few more times. Okay. Okay, this is switching up my notation. Okay, so okay. Yeah, this switches my notation by a lot, and I need to see if I need to adjust my results from that preceded. Yeah, look at it. It's using the union. I'm using this here. Oh man. Oh man. Okay. I think I'm gonna have to rewrite both of these things. Am I even gonna get to measurable functions today? Okay. Instead of writing this, I'm gonna write this. Let this set AX, X and R. Maybe I can still keep this actually. Write this as X and R, AX. Okay, A and B. I'll write this like this. Or the intersection. Okay, I think this is better. XB and E. Okay. I have to erase this then. What the heck did I do? Okay, so if X is an E, then X is an R. I need to rewrite this result. My gosh, I'm finding so many things wrong. Maybe the collection of sets AX, R. Okay. Okay, since so then x is in R, since x minus x is equal to 0, which is contained in Q. X is in the set. It needs to be in E2. Wait. X is in E. Oh, okay. Oh, X is in this set, okay. Oh, X is already in E. What the heck am I thinking? So it's in both. So X is in this intersect E, which is equal to AX. Thus X is in the union. Okay, this is not bad. This is better than, I feel like this is better than what I wrote before. The union of AX. Okay, so now we let X be in here. So let X be in the union. Okay, so then some should I use Y? So this element is in the union. Is using X twice problem here? I don't think so. And for some X in R, X is in AX, which is equal to less X is in E. So I didn't even do the subsets, but whatever. I think it's just extra writing that I feel like I shouldn't have to write. But I should if I want to be proper. So we applied containment in both directions, so that means that E is equal to X. Okay, that's the first part. It's much cleaner. Any fun plans for the weekend? Not really. I don't think so. I might visit an old professor of mine either tomorrow or maybe later today. I still haven't decided. But don't really have any other plans. I'm planning on streaming tomorrow. Um, yeah, I think it's just kind of like it's like any other weekend. What about you? Let's go get boba. Are you even in SoCal? The A B B N A. Okay, I'm gonna rewrite this. Sunday stream? Yes. I streamed last Sunday. I'll stream tomorrow. I want to stream more. I was gonna stream yesterday, but I woke up too late and then I had car issues, so I had to kind of like address that. And so I just kind of like by the time everything was done, I was just kind of tired. I almost streamed last night though, but I chose not to. No. The heck? Then why are you asking me? Let's see. I think in this case I can just suppose. Suppose A is equal to B. Then we're done. Suppose A doesn't equal to B. But soon I'll swing down there. But me, just chill and some recovery. I see, I see. Just chill, recover from the dentist. Wait, don't you work today? I thought you work on the weekends. Suppose this is not equal to. So we're doing a contradiction. I think this is still gonna work. Contradiction. If you have no idea what to do, contradiction is usually a good strategy. Suppose A intersects B is not empty. Then there exists an X and A and X and B. So that's because it's not empty. Yeah, I think this is fine. I don't think I need to change any of this. Yeeth. Nah, I'm off until Tuesday. Well, at least you got a weekend. That's nice. I prefer having my weekends free because that's when most people are free. I feel like I could be talking out of my butt, you know? So like if you were not free on the if you were free on the weekdays, then no one else is really free, and then it's more lonely, I guess. Yeah, this is still fine. Yeah, all this is still fine. I'm so happy that this still works. Awesome. So I just showed these properties. Well, you write these two properties about this collection script A. I'll call it script A, which is used in the Vitali theorem. It's not proved, but it's used. So for completeness, I prove it. Have you grind unite? Are you grinding unite still? Oh man, I can't even think about playing that game. I play that game if I want to suffer. If I did something bad and I feel like I need to atone. Okay. Nice. Yeah, my schedule's all over the place, but weekdays are free at the moment. Nice. Awesome. Uh, because I switched the notation to this, now I need to now I need to go through Vitali again. Fuck, man. I went from 1520 to 1470. Dang. Yeah, I need to be careful. Shouldn't be moving these things around. So if the reasoning for the subset's still fine, it's the way I described this set. This is now AX. Okay, so I'm driving back in a bit. If you're still on, I'll look. If not, I'll see you in Yugi. I mean, Resi stream. Have a safe drive. Where were you actually? Were you still at the dentist? The heck? By a choice, but I actually have a choice. There exists a choice set. Okay, that's fine. Comprising exactly one member from each AX and this script A. By result 2.47, this is equal to this. So okay, so result, we just did that. I was in SF. Oh, okay. We claim that CE is not measurable. Okay, this is fine. Oh my gosh, what is this? Why is everything shifted? Like this is specifically shifted for some reason. Um, okay. Infinite, blah 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 blah. Irrational, that's fine. This is fine. Oh yes, thank the Lord. I didn't really depend on my notation in the mission. In the mission. What do I even mean? Submission and location. Oh, it's not even. I'm not even done with the proof. It's like still a chunk left. Okay, by 2.43. Oh, that's way above. That's fine. I don't think there's anything wrong with that either. It's bounded since CE is bounded and measurable. It's disjoint bounded. This is blah blah blah. Note that this is an E. This is fine. Okay, this is fine. All right. Yeah, I think I'm in the clear. I don't have to worry about this. For a second, I thought the notation was just going to ruin some of the proof. Okay. Nice. And then we can move this up a little. And then move this. All right, we're good to go. That's fine. That would wrap up the measurable stuff, the measurable set stuff. Uh, the next thing is the Cantor set. I didn't really feel like going through the Cantor set. Was not motivated enough. But if I ever need to for future reference, I will just go back to it and prove some of these results. But I'm choosing to skip it. So we're skipping this, and then we're going to measurable functions, Lebesgue measurable functions. So that's this. And I've already done some work on it. So how does this book define? A function is said to be Lebesgue measurable or simply measurable provided that its domain E is measurable subset of R, and for each real number C, there is a set X and E for all f of X less than C is measurable. Your local turnip, how's it going? So that's the definition we're going with. I just kind of rewrote it. So the set, it can be rewritten as like the inverse image. And then the first thing that so this book doesn't do this, but there are equivalences that you can show. You can show that all of these sets are equivalent, or all of these consequences are equivalent. If one is measurable, then the other ones are measurable. Good, thank you. How are you? I'm good. Just working on measure theory. Okay. So I went through this. This is fine. This is just properties of measurable sets. You're basically using properties of measurable sets and the properties of inverse images and how intersections and unions interact. So if you take the intersection of an inverse image, the intersection can basically go inside. So I did this. Basically, you only have to prove half. I think these two. So this one and this one. Prove these two. And then you can use the complement for the rest. Now you prove these two. You prove these two are equivalent, and then basically the complement properties of measurable sets gives you these for free. Okay. Now here's something that I was working on before. I haven't finished it yet. So it turns out that if your function is measurable, you get that the inverse image at a point is a measurable set for all points in the extended reals. But it doesn't actually go in the other direction. If it went in the other direction, it would be listed here as like number 5. But it's actually it just works in the forward direction. So that's if we define our measurable functions using this using sets that using these types of sets, then you get this for free. And I think the same thing is true for these. I was still thinking about this, but this also only works in the forward direction. So if your function is measurable, then this is a measurable set. This is a measurable set, and this is a measurable set, and this is a measurable set. But this being a measurable set does not imply it does not imply that these are measurable, which is interesting. As far as I can tell, I haven't confirmed this, but I can't figure out a way to construct. I can't figure out a way to construct these sets from these. It's not obvious. I've worked on it for a while, and I don't think there is a way to do this. And so there should be a counterexample. But anyways, so I was in the middle of proving this. And this is also part of the... Oh, it's not even in this book. It's in the older edition. Interesting. I think it's interesting what they choose to cut out from the newer edition. On a side note, if you actually are not in the extended reels, then you can actually show that these are all equivalent. And I know this because I've shown it in the Axler book. It's like an exercise in the Axler book. So you can actually show that these are all equivalent in when the codomain is just the real numbers, not the extended reals. So it's the fact that you have these extra infinities like these extra infinities in the codomain that kind of ruin um, everything for these guys to be included in the equivalence. Okay, so this is 5. Okay, 2. Okay, so yeah, this is fine for part 2. Cut. So we start that f. So f is measurable, gives us this measurable set. So if f is measurable, we get this. And since this is true, we also get this from the equivalence of measurable sets. And then what we can do is we can just let A be less than B. And then we can take the intersection, basically. So we take the intersection basically goes inside, and then we take the intersection of these sets, and the intersection of these sets is the open interval. So right here, we're taking the intersection of these two measurable sets, right? These are measurable sets. And so we know the intersection measurable sets are closed under intersections. And so this is measurable. And this was my attempt. This was my attempt to prove the reverse direction. Supposing that you had this as a measurable set, I was trying to get to this, and it was like mission impossible. So I'm gonna delete this. And then I'll just start with 3. So this is not in the book, by the way. Like, this is something that I added because it does get used. It gets these consequences get used in this proposition 2. So I figured I should just have this proved before I do that. And I don't even think it's an exercise, actually. Let's see, is it an exercise? No, it's not an exercise. It should be like exercise 1. This is basically this is kind of like a problem that is having you go through property 1 and basically determining whether you can go the other direction, which I'm pretty sure you can't. Okay, let's finish this proof. So we have closed. Okay. Since f is measurable, gotta be more clear. I wasn't really clear in the last two. Since f is a measurable function, f inverse from a to infinity and f inverse from negative infinity to b are measurable sets. And let a be less than b, then f inverse of a to infinity intersect f inverse negative infinity to b, that's equal to a to infinity intersect negative infinity to B. And we know that's just equal to A to B is measurable. By closure of intersection. Dang, pure math is scary. That's what I thought before. The more you work on it, the less scary it becomes. And then you see something else that's even above what you're working on, and it's also scary. So I guess it never ends, to be honest. At least not for me. Is measurable by a closure of intersections. Yeah, and that proves this one. That's 3. Okay, and then 4 is fine. I think I'm happy to stay within the realm of hard, wavy, intuitive math. But respect. Thank you, thank you. Oh, hand wavy. Yeah. It's like hard wavy. I was like, what the heck is hard wavy? Hand wavy. When I learned physics, that's kind of like what I had to do. I had to do a lot of hand wavy stuff. But I'm slowly but surely getting to the point where I don't have to wave my hand too much. Just to divide both sides by dx. Hey, at least you're aware that there's something interesting going on there. I think I feel like most people are not aware about this sorts of nuances. Let's see. What do you study? If you don't mind me asking. Let's see. So 4. Okay. It's gonna copy all this. Since f is a measurable function, this is basically using, what the heck is this? I'm in electrical engineering, and the math we do is even more hand wavy than physics. Trust me. That's funny. Hey, but if you were to show that to any, I wouldn't say any. If you were to show that to someone in physics, the stuff that you're working on, they're probably gonna be like, "What the heck am I looking at?" F is a measurable function. F inverse of a to k is measurable. Are you almost done with EE? Where are you in that process? So measure. This is a measurable set by 2 of this theorem. One more year to go. Nice. Almost there. I have a friend that graduated in EE, and a lot of the later stuff involved a lot of like programming, like a specific time of programming. I don't know what it was. For EE standards, I'd say I'm pretty into math, like signal processing. Yeah, and communication theory. It's pretty cool to me. Nice. Yeah, those are all those terms. Yeah, when I hear that, I'm like, EE. That's EE right there. Of this result at k be an integer, or not just an integer. We can let it be a natural number. Then we can do the union. K is equal to 1 to infinity. But I mean, my understanding of Fourier analysis is probably very different from yours. Maybe. I tried to explain. If I try to explain, you hear some kind of K-pad gruntling noises. That's funny. There are a lot of. If I were to, there are a lot of details. Um, like there's like two ways to look at Fourier analysis. You can think of it as like, in terms of like in the usual practical sense when you're looking at like signals, and you can think of it like when you're looking at it from like a mathematical pure standpoint, where it's like just a bunch of properties and convergence issues. I'm here early. I mean, when I first learned Fourier analysis, it was like I just had to learn like all the common properties, like the derivative properties, the convolution stuff, um, some of the common Fourier transforms, and then I basically saw where they're applied, like in quantum mechanics or in wave optics. But I think I would say if I at that point I wouldn't say I wouldn't know what Fourier analysis was. But now, but now I think my intuition about it is definitely improved, but it's still not complete. That's eventually going to be my target, probably a year from now. I'm going to be working on harmonic analysis, which is kind of like the more general theory for Fourier analysis. Yeah, Fourier optics is cool, definitely. Anything that has to do with wave optics, I really enjoyed. By the way, Rezi, how you doing? You just wake up? It's like, dang, it's like 6 o'clock for you or something like that. Like 2 hours ago. Relax. Hey, bro, I don't know. Your time is different from mine. I'm in the. I moved an hour back or some shit like that. I don't even remember these days. Rezi-san, just working on album art. Nice. I have no idea about the mathematically rigorous approach to Fourier analysis. For me, it's pretty much goes like I have a signal, I need to analyze signal properties, slap the Fourier transform onto it, consult lookup table, plot. Honestly, that's most people's experience, and honestly, that's good enough. That is definitely good enough. I think for, if I remember correctly, for most real signals, you don't really have to worry about convergence. I could be wrong. I feel like I've heard that somewhere. But that's the common issue with well, that's a concern in Fourier analysis. Also, I heard that it's an even greater concern in Laplace for Laplace transforms. But I haven't really looked into that. Measurable. Yeah, they have no imaginary components. Simplifies a lot. Yeah, yeah, definitely. By closure of union. If you ever, I mean, I don't know if you ever want a rigorous treatment, but if you ever want a rigorous treatment on Fourier stuff, this is my, no, this is not it. This is definitely not it. This is the recommended book for me. Um, Granted, you would need to know some analysis, but this is like probably like the best book in my opinion on Fourier analysis. Obviously goes over Fourier series, go over the convergence issues, um, applications, extensions to higher dimensions. Yeah, there's a lot of theoretical stuff here. But that doesn't necessarily mean it's gonna like, doesn't necessarily mean you're gonna be like, oh, now I know everything about Fourier analysis. um, at the very least, if you get through this book, you'll know like a lot of the properties and kind of like the things you need to check for. But yeah, this is a fantastic book. Probably the best out of the series. There's like four of these books. I think this is like the best one. Is the first book of the series. I see a book I will never read, but will save in my library. How you doing, Joseph? Those books, I mean, those books, um, you may never think you will read them, but you should definitely save them in case for some reason you do have to read them. It's good to have like an archive of good references. But what may be good for me might not be good for you. That's another thing you have to think about. Um, Similarly to 4, for all k and the natural numbers. Okay. Oh, wait, I'm deleting the wrong thing. Hello? The union from k is equal to 1 to infinity. Negative k to call this b. Well, let's just call it a. It's equal to inverse of negative k to a. So it's just equal to negative infinity to a. Is measurable. Is a measurable set. By closure of unions again. So we basically got all of the whole point of this was to show that all the intervals, all the inverse images of the intervals are measurable sets, assuming that f is measurable. Mechanics exam next week, but still haven't studied because I keep sleeping. Dang, I know that pain. That happens to me sometimes. What is your exam covering? Okay. The discrete Fourier transform and the Heaviside step function are not mentioned in that textbook at all. Those are incredibly important for EE, but I guess that doesn't make much sense. Yeah, actually, no. Actually, you make a great point. It's not in that book. I swear, it should be in there. Heaviside function. I'm almost certain a Heaviside function is in here somewhere. I swear it shows up in here. It had to be in chapter 5 somewhere. Okay. So they have a Gaussian, which is obviously important for Fourier transforms. Um, hmm. really not in here? I could be mixing this up with another book that I went through. Because usually it's always customary to like go over like just a few common examples that of transforms that you had to do. And that's always one of them. But I think you might be right because it's like more theoretical. It might be it might not even have that as an example. Just the bell curve because the Fourier transform of it is just itself, right? So like it's like a good kernel. Let's see, what the heck, man? It's right here. I mean, they don't call it the Heaviside function, right? Isn't this it? I think this is. This is this function right here is the it's not specifically the Heaviside function, but it's a step function. So it's like 0 and then it jumps up to 1 from the interval -1 to 1 and then it jumps back down. Yeah. Yeah, it's like a variation of the Heaviside function. Imagine not giving. Yeah, exactly. It should honestly be in there, but I'm sure Stein like has a reason for it. He's like the expert in this stuff. This is like his field. This is his like jam right here. Like whenever I see this H, I'm just like, oh, there's the Heaviside function, but it's just the heat equation. Gamma function. Yeah, there's some typical examples in here. Everything is still statics. What the heck? Statics? I forget which version of mechanics you're doing. Heaviside forever shunned by pure math elitist community. what, what book is that? Sorry, I wasn't paying attention. It's the Stein Sikarsky. It's there are like 4 books of that they made from the lectures, and the first one was on Fourier analysis. Heaviside is in the 3rd book of the series. Is it? The thing about these books is that they bring up the Fourier transform, or they bring up Fourier analysis, but specifically Fourier transform. Like in the other books. Where is it? It's not. Oh, there it is. Heaviside function. Yeah, because this is a common example in measure theory for integration. That's the reason why he's using this. I think it has to do with the delta function. There you go. Yeah. So there's a very interesting like there's a very interesting um, consequence of the generalized integral when you start working with the delta function. But it should be. I mean, why is it not? It should be in like. It should definitely be like explicitly shown in the first book. It's 4 books I'm not going to read. This is the measure theory book, by the way. This is basically the stuff that I'm working through right now. Um, Occasionally I'll reference this book, but it's not my priority book. It doesn't present the information the way I'd like it to. It's very like fast and loose. But it also shows up in it basically shows up in um, like the transform shows up in this book, which is a complex book. I think it's even has its own like chapter. She integrals. Yeah, there it is. There's the chapter on the Fourier transform in complex analysis. Page 285. Was I on that page? Won't read it anyway. Let me check if I was on that page. It's a lot. Like, there's just only so much stuff that you guys like that a human being can learn. It's just only so much stuff. What the heck? Yeah, 285. I'm like clicking it, but I'm like, you literally type 285. I'm just like, oh man, my brain is mush right now. Heaviside was an actual genius, though. I think he was also the one who invented a current popular form of Maxwell's equations. Was that Heaviside? I vaguely remember that. That sort of that fact. I had you in the background because we ended up going to the neighborhood city, and my mom and aunt were like, "What are you listening to?" I said, "You were my math teacher." He was completely self-taught or something. Yeah, well, back in those days, self-teaching was like a more like like feasible thing to do. Classical. I know you're doing classical, but like which classical? Because if you're in undergrad or if you're doing an undergrad sequence, um, you you potentially can take you typically take classical twice. You'll take it the first time um, using typically books like Sears and Zemansky, Holiday Resnick, and there's another book. Some other dude with a G, I think is his name. Like this book right here, the one that says University Physics. Like this is what students would use when they first take mechanics for the very first time. And then if you're learning it for the second time, then you would use something like a Taylor, um, which is this one. You would use something like this if you were to look at it again. I remember using statics the first year. I vaguely remember stuff about pulleys and trusses. Yeah. Yeah, you wouldn't believe how many problems I've had to solve for pulleys and trusses. Is insane. Thank you for showing the cover. Yeah, of course, of course. Good thing the professor decided to remove harmonics from exam next week. Else I'm going to be so fucked. Yeah, that's a lot. What is it? Bro, look at the bootleg way I have to freaking read the comments. It's ridiculous. Actually, I'm not even looking at this computer. I can just look on OBS. All human beings. Direct delta function is such a cool function. Discrete time signal analysis wouldn't exist without it. Yeah, it's very awesome. It's very cool. Like the first time I saw it was in E&M, and it was basically like the missing piece for um, Gauss's law. It was very interesting, and we basically learned how to rewrite certain distributions because of like the singularities that occur. Although there isn't a debate if it meets the definition of a function. Isn't there a different? Yeah, it's not a function. It's a. It's supposed to be something else. It's called the. Um, I always forget the word of it, but it's not a function. It is a. I don't have the book in here. It's like a separate class of things that. Um, where the heck is it at? It's if I had the fourth book on me, which I don't, I can tell you what it's actually called. Um, Now you got me curious. Okay. They're called um they're called generalized functions or yeah, they're called generalized functions or distributions. The term that they use is distributions. So there's like a whole different framework for them. Um, there's a human being. We all are. You're you as a human being. Use vector operations like divergence. Oh, okay, okay. For that, my EMAT course would have been so much worse without it. Yeah, distribution. I should have freaking. I should look at the comments of the chat. I would have if you were to have if I would have looked, I would have recognized the word. Physics I currently using Giancoli. Oh, his recommendation for Dr. Gold. That is the first look. That's similar to the one I just showed you, the this one right here. That's similar to this book. It's on the same level. So many textbooks. Yes, it's way too many. I got a copy of the entire series in one file. Nice. Yes. Don got photos from Japan in his server. Nice. I'll check it out soon. I was actually supposed to go to Japan in the spring, but complications. Eventually, I'll go there. uh, with all your files, we can reboot Pirate Bay. Are they pixelated? Wait, the PDF files? I hate that this is. I think this is actually pixelated. Even all the photos from Japan. Oh, but this is actually looking pixelated though on your note. And if you actually get the hard copy, it actually looks pixelated too. Japan, say less. I wish I could go to Japan. Just too poor right now. Yeah. Uh, I'll take a look what it posted. Nice. Look at all those tourists. Sorry, I know you guys can't see what I'm saying. Interesting, man. This makes me want to go to Japan so bad. One of these days. One of these days I'll be able to go. Okay. Um, I'll go on your luggage. Me too. Let's see. Okay, I've streamed for a while. I'm debating whether I should go through this theorem, but it's like spent so much time already doing the other stuff. Let's see. How long is this? It's a very short, but I said that about the first thing I did today, and I ended up spending an hour on it. If the inverse image of each open set is measurable, conversely suppose F is measurable, let O be open, countable union of intervals. Yeah, and so this is basically going to use the results that I just proved right now, because it's going to use open intervals, and then you're going to use the union properties, and then it's going to construct O. Yeah. I'll do this tomorrow. Um, I mean, the other stuff is plain Unite. Go to Japan in the guise of a sandwich PhD program. Losing in Unite. Yes. Playing that game is just so it just destroys the mental. If you know it now, if you do it now, future Ren doesn't have to deal with it. But if future Ren doesn't deal with it, future Ren deals with something else, which is proposition 3 and 4 and 5. Also, there's no rush, to be honest. Knowing the behavior of people in Unite made it easier to accept election results. Yes. There's just, I don't know. There's too much things to handle. I draw a lot of analogies from my Unite randoms and my real life randoms. Oh, man. What should I do? Any ideas? Should I end? Should I play Pokemon Unite? Uh, do I even want to play? I could do it. Future Ren will be bored. And this Prince Graph. We know who will, who we know who MA was gonna vote, but damn, would it hurt to actually suspend classes for election day? 24-hour stream, definitely not. I can't see those freaking. I can't see that stuff from OBS. Pants grab isn't even an emote. Oh, oh, there you go. I was like, what the heck? There's the pants grab. I could have sworn I did that. I could have sworn that was one of the first ones I added. All right. Oh yeah. Have fun with that. How about Wench? How about that, Poncho? Oh my gosh. I forgot that's how it looked like. Oh my. Okay.